Hi, this is Vinay, and in this ICP8, we are going to do the variational autoencoders. In this, we are using the same data as used in the ICP that is explained in the class. And the main change is that we are going to add two more layers to the encoders as well as the decoders. So after that, we are going to report the findings and explaining why we have added those two layers to the both the encoders and decoders. So let's move into the code. So first thing here we are doing is that here we are importing the libraries. So in the first step in importing, we are importing all the required libraries like Keras, and from Keras.layers we are importing convolution 2D for the building the model, convolution 2D transpose for the encoder, input, flat and dense, lambda, reshape, dropout. So these are all we are importing it from the Keras.layers, and we are using the batch normalization. We are importing the model. One more thing is that here the data set that we are using is the MNIST. So from the Keras.data set, we are importing the MNIST, and for the loss function, we are importing the binary cross entropy from the Keras.losses. So we are importing the NumPy, and then for the plotting of the graphs, we are importing the matplot.pyplot. So the MNIST here, it is a data set that consists of 28 cross 28 pixel images, which is basically a handwritten digits. So it's numbers. So here what we are doing is that here we are splitting it into the train and test. So here by using the dot load function, we are splitting the data into the train and test. Then we are printing the output. So here we can see that for the input train one, the shape is that it consists of 60,000 images of 28 pixel, and the this train one is the labels of that, and the input test one. Here we can see it consists of 10,000 images, and here we are the same 28 cross 28 pixels, and target test one is the labels for that. So now what we are doing is that since we have a large amount of data, we are reducing the size. So for that, we are considering only 10,000 images for the input train and target train. And for the testing, we are considering only 1,000 images. So then we are printing the first 10 images. So here we can see this is 5, this is O, these are 4. This is basically, it's kind of handwritten alphabet numerics. So these are the 10 images that we have used. Then I think we need to run this. Yeah. Now after we have reduced the size, right? So we are just displaying the shape once again. Here we can see now these are of 10,000 for the input train, and the first it's for the testing it's 1,000 images. So now we need to uh, initialize some of the variables. So here we are initiating the batch size, number of epochs, validation split, verbosity, latent diminution, number of channels. And here we are storing the image width and image height as well. Next, we need to reshape the data. So here we are reshaping the data so that it can take 28 cross 28, and x is the number of samples in either of the training data or testing data. We can also set the input as 28 comma 28 comma 1 as an input shape. Next, we phrase the number as a floats, which presumably speed up the training process and normalize it, which the neural network appreciates. So first we are reshaping, then we are parsing, then we are normalizing the data. So normalization is nothing but here we are getting all the data into the range of zeros and ones. So we know that pixel maximum storage is 255 is a large number of pixels. So we are dividing it by that value so that every image will be of this range between 0 and 1. Next, here we need to create the encoder. So for the creation, it's kind of three-step process. First, we need to define it. Then we need to perform on that the reparametrization trick. Then at the last, we need to initiate the final step is that we need to initiate them. So now we are doing the encoder definition. Here we are creating an encoder by giving some values. So the first step here is that we are giving for I, in I we are giving the shape as well as the name. In the CX, in the first layer here, we are in the first layer, we are using 8 filters, kernel size as 3, strides as 1, padding as same, activation as reload. So here we are using the convolution 2D model in building. Then we are perform the batch normalization. Then we are adding another layer with 16 filters and rest of the same parameters. So one more the main change that we have done is that we are building the layer with 32 filters, so that the more the number of filter, it's the more the model is powerful, so that when we go to a larger image, the prediction or the accuracy of the model will be high compared to less number of filters. So here we have built the other layer with 32 filters, then batch normalization. Then we are using the same 32 filters, then batch normalization. Then we are flattening it. Then we are using the dense function, and then we have added the dropout layer, because when we have seen the graph, we know that, I mean, there was an overfitting problem uh, that I will show in the Word document. So when we have plotted the graph, here we can see that there is a huge problem of the overfitting. So in order to overcome that, we are using the dropout. After using the dropout, it was clear that there was no overfitting problem. Let me run this. So we are done with the encoder definition. Then now we need to get the 2D shape for the convolution 2D transpose operation in decoder. So now convolution V shape has this k dot init shape of CX. Then we need to define the sampling with reparameterization trick. So we are basically defining a function for the reparameterization. Then we are using the reparameterization trick to ensure the correct gradient. So this is done by using the lambda function. Then we are initiating the encoder. So this is the model that we have built. We can see that, and this is the model which has a total parameters as a 5,17,432, non-trainable are 216. So then we are creating the decoder. So it's almost the same, but here we use the convolution 2D transpose, because when we have come across this encoder, the shade is somewhat reduced, but now we need to increase the size. So we are using the convolution 2D transpose. So we have added the convolution 2D transpose with 32 filters, and then we have added the dropout here as well. So these are the two extra layers that we have added. So we are defining the decoder. Then we are initiating the decoder. This is the model that we are using. Then instantiating the VAE, that is a variable encoders. Next, here basically we are compiling the VAE and we are training the autoencoder. So for the compilation, we are using the optimizer as Adam, loss as a binary cross entropy. We can use other as well. And here, in order to show the dropout, I am using the metrics as accuracy, and so that we can plot a graph for the training data and test data. So I have given the metrics as accuracy. Then I have stored this the evaluation in the history variable. So since we are given the epoch as 50, it will run for the 50 times, and we can see this. I've already ran this one. So this is the values. Then we have plotted the graph for the accuracy and loss as well. So here we can see that there is no overfitting problem compared to the model that we have used without the dropout that was said in the class. So here we can see the overfitting problem is no more. Next, we need to visualize the results. So we are building a new definition for that. We are basically using the viz latent space and viz decoder. So these are the two functions we are using. and we are plotting the results. So here we can see this is the graph for the input test and the target data. Then we are visualizing. So here when we have the numbers are in such a way that it can be easily predicted, since we have added the new filter as well as we are adding the new dropout. So the numbers are easily visible with this. So that's the end of the ICP. Thank you.